Okay, with that, the first talk is over. Now we are about to start the second talk on fundamentals of machine learning by Dr. Vinay Raj, Assistant Professor, Department of CSE, NIT Trichy. So, Raghunandan sir, if everything is okay, shall we start the second talk?
Sure, sir. Sure. Please start.
Okay,
Okay, sir. You can start, sir.
right. So, let me please introduce the speaker of the second talk on fundamentals of machine learning, Dr. Vinay Raj. Dr. Vinay Raj is currently working as assistant professor in the Department of Computer Applications, NIT Trichy. Uh, Before joining NIT Trichy, he pursued his postdoc at University College Dublin, Ireland. He has a total of 8 years of MTech from BITS Pilani. His PhD thesis title is Studies on Migration of SOA based applications to Microservices Architecture. His research interests include software architectures, microservices, serverless computing, cloud computing, and machine learning. Currently, he is supervising one full-time and four part-time PhD scholars at NIT Trichy. He has worked as senior software engineer at Capgemini and software developer in TCS Hyderabad. He also served as soft skills trainer in Jawahar Knowledge Center, which is popularly known as JKC at Hyderabad. Hope Vinay Raj sir's lecture would be very much useful to the participants. Thank you. It is now over to Dr. Vinay Raj sir. Vinay Raj sir,
Thank you so
please
much.
take up.
Thank you, sir. Good evening, one and all. So myself, Dr. Vinay. So today we'll be discussing about fundamentals of machine learning. Before we go into the concept, I would like to talk about some facts. Like the previous session, you have enjoyed a lot, and I see a lot of good feedback being shared. So it was so thrilling and interesting to know where all we can apply machine learning. So to visualize it, to see it, it's very good. We all felt happy that a lot of improvements are happening in machine learning. But as a developer, as a ML researcher, we have to design models. So how do we design the models, right? All those products which you are seeing are being designed or developed by some of the developers or maybe researchers who are working on this field. So in this session, I'll be taking you towards those important points or those fundamental concepts which will help you in understanding the remaining 5 days of this workshop. So any query in between, you can stop me and ask me. I'll just go through the slides. So today we'll be discussing these 4 things to learn machine learning. Keeping in mind there are a lot of students. So to learn machine learning, what is the roadmap and what career opportunities we have here in India. Then fundamentals of machine learning with the definition, and the most important, mathematics for machine learning. And then ML algorithms in simple terms, because in the next whole week you'll be learning a lot of ML concepts. So those I'll just introduce here. What is the meaning of each algorithm or each technique, how and where it is useful. The basic things only, not in depth of those ML algorithms. So this is the roadmap of machine learning engineer. Somebody wants to work on machine learning, need not be engineer. It can be data science, data scientist. We have a lot of roles in that. So if you want to become a machine learning engineer, the first and the foremost important point here is mathematics, right? So a lot of scientists say that machine learning is nothing but mathematics. There are a lot of memes and trolls on machine learning, that it is not new. When this was introduced, till a lot of senior professors say that this is all existing, it is not new. Only thing we have added are the flavor of computing by writing algorithms using the Python programming, right? So this one point I would like to focus. If you are very strong at mathematics, we'll see what all concepts of mathematics. If you're very good at mathematics, then the remaining rest all flows well, because if you want to understand the linear regression, you should know about the this regression analysis in mathematics, or you have to know about the linear algebra concept in mathematics, right? Same way, if you want to know about the probabilistic regression models, you should know about the probability models in the mathematics, right? So this lays a strong foundation for the whole ML roadmap. To understand any of these concepts, you should have very good mathematical concepts. So we'll explore what mathematics are required for machine learning first. So different career opportunities, lot of terms synonymously used: data engineer, data scientist, ML engineer, ML developer, research scientist. All these things exist. But if you see the general ML workflow, like in software engineering, we have software development lifecycle, we have some flow: requirement gathering, analysis, testing, design, testing, and then we go for deployment. In the same for machine learning also, there is some flow, there is some process. So first the data ingestion, that is data collection, then data validation, data preparation, doing some statistical analysis here, then going for model training, model evaluation, model validation, model serving, and then this again a generic flow like how a software is built. So these different roles exist. If you are working in these phases, you will be called as a data scientist or a data engineer. If you are working in these phases, you will be called as a developer or an ML engineer or a research scientist who works on building models and evaluating the models. So there are a lot of career opportunities. We know it is trending in India. So specifically, if you want to understand what is the difference between different roles, so the skills lies little different. Here, if you see, let's start from data analyst. If you see, the programming knowledge is little less here, but we are using lot of tools, BI tools, right? Excel, Tableau, Power BI, Pandas. So all these things we are using here. Same little advanced in data scientist. We use some of the modules of or libraries of the machine learning here. So these are the actual core Python libraries which will be using in ML. So these different kinds of roles are possible depending on the skill set. That's why in this whole flow, the first half focuses on the this first half focuses on the data science part, and this focus on the machine learning part. And here end we have ML ops, right? So these three different phases, either you can focus on this. If you're looking for a job, you can focus only on these steps. You can become a data engineer or a data scientist. If you focus only on these steps, you can become a ML engineer or a ML developer, right? So I will just quickly introduce this paradigm of artificial intelligence with an example, because frequently we will be using these terms in the coming sessions. Though you got an awareness about AI, machine learning applications you have seen, but let's see what actually it does. I'm talking in the perspective of a developer. When you are working as an ML developer or an ML researcher building models, you should know the differences between all these things. When I have to use GenAI, what is LLMs, what is the relation between all these things, and how do they differ to each other. Let's take an example of teaching a robot how to bake cookies, some biscuits or maybe chocolates I want to bake, some cake I want to bake, that I want to teach to a robot. This example we'll be considering so that you understand about all these terms easily, how they are linked to each other. Okay, so I'll just skip the first part, AI part. I'll just skip this. I'll just go to the second one, machine learning, right? So I'll come back to that AI. Now my task here is teaching a robot how to bake cookies. So what is machine learning? It is teaching by examples, meaning you in front of robot, to the robot you will show lot of cookies. You will show, right? You see, you will show 100 batches of cookies, just an example, with the labels good or burnt cookies. So that robot will see with the labels, there are some cookies, this cookie, this is one cookie which is good, there is another cookie which is all burnt. So we will show 100 such cookies to the robot, and it will learn from that, right? So machine learning, the key idea is uses data to train the robot to make predictions or decisions. So in machine learning, for this problem of how to bake cookies, we will show the robot some cookies which are good and some which are bad. Based on that, it will try to learn. So machine learning, so it is learning, right? So the robot learns from this labeled data and predicts how long to bake future batches for good cookies. It is learning from the data. Next, if you talk about neural networks, right? What is the difference between neural network? What is the use case of this? So the robot's brain for learning here, meaning like human beings, we think and analyze. Same way that we are talking about robots' brain here. Okay, so you see what we are trying to do. Neural networks are the robot's brain that learn relationship between the inputs, the outputs, right? So we generally in neural network, it is all about mimicking how humans learn. So using neural networks, you are trying to train the robot like we learn. How do we learn generally to bake cookies? What is humans, how do we learn it? By seeing, by watching some video, or by understanding, by reading some script, we understand how to prepare cookies. In the same way, we are teaching or we are training the robot. For that, we use neural network. Machine learning, we were just showing it which are good and which are bad. We are not exactly telling how to prepare it. Okay, so generally in neural networks, we have 3 layers. Input layer is about the baking time, meaning the input which I'm giving to the model. Baking time, the temperature, the sugar level, these are the inputs. Hidden, and okay, you see the output. Input is given, output is given. That is good cookies or bad cookies. If these 3 are given as the input, that is the baking time, the temperature, and the sugar level, right? So output is good cookies or bad cookies. But internally, there is something called hidden layer, right? So adjust weights to find relationship. Too much sugar burns the cookies. So that depending on that, it will adjust accordingly and give the output. So again, let's summarize. Machine learning is all about, here we teach by example, but here we mimic the human brain in the neural networks. Deep learning. So layered thinking of complex baking. In deep learning, what we do for that robot, we'll actually show some pictures. Okay, we will show the image, we'll show one picture of a cookie. So in deep learning, what the robot will do, it will detect the edges. It will see, okay, this is something like this in shape. Then it will identify textures, cracks, burn marks. It will see some scars on that biscuit or the cookie. It will try to understand how is that cookie, what is the structure of that, how is the edge of that, are there any scars or marks on the cookie, right? Finally, it will decide whether it's a good or bad cookie. So here we are giving the input as image. So that's why deep learning uses multiple layers of neural networks from images. Okay, so it will get the data from the images. So idea here is to such as visual details in cookies. Okay, so in deep learning, we have to, that's why we say deep learning is mostly used for computer vision. Images it will see, it will understand, and it will take a call on that. Generative AI. Here, what is this word generative AI? Same example of teaching how to bake cookies. The robot creates new recipes. What does generative AI do? It will study hundreds of cookie recipes. It will study the different existing recipes of the cookie making, because in India we have different style, in some other country there is different style. All those styles of preparing cookies it will learn, and generative AI will invent a new recipe, something like this, double chocolate with a hint of cinnamon. So it is generating a new recipe after learning from hundreds of such existing different recipes. So that is about generative AI. And the last one, LLMs, large language models. We are talking a lot about LLMs. So in this example, how it is used. So the robot learns to chat about cookies. In this, I'll just quickly summarize that. See, you are asking a question, how do I make chocolate chip cookies? It will tell you how to make it. It is giving the instructions. So this is about LLMs. Now, if you summarize all that, if you just go back and see all those phases. Machine learning. Machine learning has a limited set. Here, it can only, this in machine learning, it can learn through examples. We will show some good and bad. It will take decision on that. It will learn by seeing, okay, this much of color in the cookie means it is good. More dark in color means it is bad. That it will learn from the examples. In neural network, what we do, we actually give the instructions. We actually train it, right? So robot's brain, like human beings learn, we will be in neural networks, that robot will be learning it. In deep learning, we give lot of neural networks. By seeing an image, it will decide that, okay, this is this should be the shape of the cookie, and the textures or some scars on the cookie, it will decide on that. Generative AI, it will learn from the existing different recipes, and it will recommend or suggest some new ones. And the last one, LLMs, large language models, these are used to talk to the robot, asking questions to the robot. How to prepare cookie, what is the texture what you have used, or what is the flour what you have used in the preparing the cookie. All that information is available, given by the LLMs. So these are some just few frequently used terms in this whole session. AI, ML, neural network. You are going to learn all these things in the coming days. Just I want to introduce this before we go and understand about the fundamentals. Right. So what is machine learning? If you see this example here, there is a small program, addition of two numbers, right? A equal to 3, B equal to 5, C equal to A plus B, C equal to 8. So my input is these two parameters. I'm writing the code, that is C equal to A plus B, and normal programming, we do this. This is normal programming approach. It will give me, you write any program, C, C++ or Python, it will give the answer C equal to 8. So if you observe, you are giving the input, you are giving the code, that user means we are giving the input, we are giving the code, the computer is giving me the output. Whereas in machine learning, I'll give the input and I'll give the output. The computer will give me the code. So that is the difference between normal programming and machine learning, right? So we are giving the input and the output, it is giving me the code. That's why machine learning is subfield of computer science that gives the computer a ability to learn without being explicitly programmed. So it will learn from the experiences and it will give us the output, whatever we are expecting, like this. In detail, we talk about three things in machine learning, right? So machine learning is all about designing algorithms that automatically extract valuable information. Now we talk about three core points, concepts here: data, model, and learning. These three are the core concepts of machine learning: data, model, and the learning. We know data is the heart of machine learning. When you have data with you, only when you have the data, then only you can build a model, and that model can do the learning process. So data is the core of machine learning. The goal of machine learning is to design general purpose methodologies. Next, model. A model is set to learn from the data if its performance on a given task improves from the data. So you should have the data set, you should have, then you can build a model, and that model can learn from the data. Now, see this small meme about machine learning. We have computer science algorithms here, CS algorithms, and we have mathematics. But machine learning, if you see, maths plus the algorithms, right? So this is very clear that mathematics is required much. A lot of definitions about machine learning. Some say mathematics is the heart of machine learning. Some say machine learning is itself is the mathematics. Okay, so a machine learning model is a type of mathematical model. Machine learning model is a type of mathematical model. So mathematics is very important, fundamental for the machine learning. We'll see what all concepts are required. So to learn machine learning, you should have good knowledge on all these. There are again 4 pillars for machine learning, that is regression, dimensionality reduction, density estimation, classification. But if you see the foundation required to understand the machine learning algorithms, to design ML algorithms, or to build models, you should have good knowledge about linear algebra, calculus, analytical geometry, probability, optimization, and matrix decomposition. So on. There are some more mathematical concepts required. So these are the basic and the important mathematical foundations required for machine learning. So why are these concepts and how are these concepts used in machine learning? I'm trying to give an overview how and where these mathematical concepts are being directly used in machine learning, or it could be an answer for why we should study mathematics for machine learning. Why everyone is telling the mathematics is the first step for machine learning. For that, we will just try to see. So these are the concepts: linear algebra, matrix decomposition, vector calculus. You have studied everything. Maybe whenever you did your UG or PG, everything is known to you. But only thing, how are these used in machine learning? That relation we will try to explore. So probability, optimization, statistics, regression, and lot of mathematical metrics are there which are used in ML and data science. So let's see why only these concepts. Why we need to study these concepts one by one. I will try to explain. So till now I have just explained you about the terminology like AI, deep learning, neural networks. What are those things? And we have seen that 4 different foundations of mathematics, pillars and foundations of mathematics. Now why we should learn linear algebra and how it is useful in machine learning? Let's see this. So generally, if you take a base case, machine learning data is again a simple data set. If you take, it could be one data set in CSV file. So it's in the form of a table or a Excel sheet. I have data with me. You might have seen different kinds of a basic simple example I'm taking. Maybe we have some student data with me, where I have student marks, his roll number, his GPA, semester wise. I have some details, numerical data of the students of our institute. So when I have this data, right, we use data for machine learning. That's why you said, no, data is heart of machine learning. Without data set, we cannot do anything with machine learning. So when you have such data with you, right, machine learning, whatever is the format, we try to convert the machine learning data into numerical form. And we represent the numerical form data as vectors. And such table of such vectors is called a matrix. So the data set what I have with me in the CSV file or in a table format, that if some of them are numerical, okay, some are not numerical, we can transform them to numerical form. After that, this data set, this whole CSV or Excel sheet of data becomes numerical data. And each column here represents a vector. So this exactly becomes a matrix. I'm talking again a base example when you have a base case data, right? So machine learning data is converted to numerical form, and we represent numerical in terms of vectors. Table of such vectors is called matrix, and study of vectors and matrices is called linear algebra. So when you should study, if you want to play with machine learning data, you should know linear algebra concept. Only then you can play much better with this machine learning. That's why we have to study linear algebra for machine learning. Next. Now, when 2 vectors represent 2 different objects in real world, we know 2 different vectors in the data set represents 2 different objects in the real world. Okay. We want to make statements about their similarity. How are these 2 vectors, V1 and V2, are they similar to each other or not? Why I have to study this? Because sometimes I may give this input to a model and I'm getting an output O1. I'm giving this vector V1 as an input to one ML model and I'm getting an output O1. And if I give another input V2, I may get another output O2. Now the point here is, if V1 and V2 are similar, if vectors V1 and vector V2 are similar, then when I give V1, it is giving me O1. it is obvious that when I give V2 also, it should generate O1 kind of output. For that, I will measure the similarity. To avoid wasting our time, we will just find out similarity between two vectors. If two vectors are similar, then only with one vector you can test your model. So the idea is that vectors that are similar should be predicted to have similar outputs by our ML algorithms. So when we talk about similarity, we study analytical geometry. We study about dot product, cross product. We study about angle between vectors. We study about the similarities between the vectors in this concept of analytical geometry. So again, what is a vector here? Vector is nothing but a part of the machine learning data. So that's why we are studying linear algebra, and this shows us how and where these concepts of mathematics are useful in machine learning. Next, then sometimes the data size is very large. Yes, so the data set whatever we have, it's not small data. See, in maybe in our academics, we see matrices up to size 5 by 5, 6 by 6 matrices we play with, finding determinant, doing some operations on the matrices. So till 6 by 6 we can handle, maybe system can handle. But if the data size is very large, 1000 cross 1000, even the computer, even the system, to perform some operations on that matrix takes time, right? But will our data set be very small always? No. Data set, as if the data set is more dimension, if higher dimension, the model will be much better when compared to the smaller dimension data. So to build a model, I should have more data with me, so that the model is predicting accurately. So for that reason, data set will not be always be a small, it will be large. So when the data size is large and the dimension of the matrix is higher, we cannot play with this higher dimension data, higher dimension matrix. So what we have to do? We have to do matrix decomposition. We have to break down that large matrix into small matrices, so that I can apply the known concepts, finding out rank, solving system of linear equations, finding solutions for a given matrix, all those determinant of a matrix, inverse of a matrix. I cannot do it for large matrices. I can do, but it will take a lot of time. To avoid that, what we can do, when you have a large dimension data with you, you can apply a concept called matrix decomposition, where we break down the large matrix into small matrices. Okay. So in this slide, linear algebra, analytical geometry, and matrix decomposition. Why? We are talking about machine learning data. Whatever data we have with us in the numerical form, we convert that into matrix. To play with matrix, we have to study linear algebra. In this, what we learn in specifically, we'll see one by one. In linear algebra, what we have to study. In analytical geometry, what exactly we should know when going for machine learning. Next. Now, we often have noisy data in the data set. What is noisy observation or noisy data? See, you conduct a survey or you collect data from students. Definitely there will be some fellows who will not be filling proper data, right? Or sometimes the data is not accurate. You see, sometimes this is maybe a age. This is the age, or this is the age. Sorry, this is the age feature. Age feature of students. It could be -1, 0. This could be X here, some 10, 20, 30. These are all valid. But if you see, there are something which are not valid. This is noisy data. This 0 age is also does not exist. Age 0 does not exist. Age X does not exist. All these are noisy data. So in the large data set, no data set is perfectly 100% correct. There will be a lot of noise in that, because the data set is not perfectly generated. Whatever data set we are having today, it's not accurate data set with us. There will be definitely some noise. So when you are having a noisy data set with you, you are trying to build a model. You are trying to build a model on this noisy data set. Definitely this model will not give 100%. No, see, this data is 97% accurate. Can you expect 100% perfect, 100% accurate model? No, because when the data is not perfect, definitely the model will also not be perfect. So when the models built on such noisy data express some sort of uncertainty, meaning there is no guarantee that it is 100% accurate. There is some uncertainty. Why is it there? Because the model is built on noisy data set. The data set on which the model is built contains some junk values. When you have a junk or some noisy data, the model is not perfect. So we talk about uncertainty. So when you talk about uncertainty, the quantification of uncertainty is probability theory. Why? You know, right? We say that it is 97% accurate, 85%. You're not sure. It is just kind of you're telling in terms of percentage. I'm 85% confident. I'm 90% confident. You are telling. You're not giving 100%. Why 90% confidence? Because the model is built on some noisy data. So when you want to quantify these kind of uncertainty, you have to study probability theory. Next, I said, right, ML models are mathematical models. If you remember, machine learning models are mathematical models, right? So maybe best example is linear regression, though I did not introduce that. We will see about linear regression, but just an example. Y equal to mx plus c is a simple linear line equation. Y equal to mx plus c. So this is actually a linear regression model. Okay, so that's what in mathematics it is called line equation. In machine learning it is called regression, linear regression model. We call this as a model here. We use the term model because we are training and building this model, right? So when you have models, there are some parameters here, m and c. Okay, so what we try to do, we want to optimize these values of m and c. For example, with the data set whatever I had, with the data set whatever we had, we got an equation y equal to 3.92x plus 7.512. This is the line equation I formed with this data set. Okay, now maybe if I try to test this model, I had some 100 records. With the 100 records of data, I got this model. I built this equation. Now I'm trying to give the 101th input and see whether this is giving the perfect y or not. So if the data is perfect, it might give, but there is high chance it may not give. So what we have to do, we have to somehow optimize this 3.92 and 7.512 such that I get the best model. So maybe I have to change this 3.92 to 3.819, something like this, and 7.725, something like this. So I'm changing these values. Either you are maximizing or minimizing it. Indirectly, we are doing optimization. So when you talk about optimizing the mathematical models, which are called as machine learning models, we use the concept of gradient. Why? We find out the derivative, partial derivative of one order, first order, second order. We keep doing these derivatives in the in mathematics. To find out the minimum, maxima, we do derivatives of that. So we call that as gradient. Gradient means derivative of a variable. So when we have to do, you have to apply a lot of optimization techniques. Why? Where do we apply optimization techniques? We apply optimization techniques to models, mathematical models. And I'm saying that machine learning models are mathematical models. For that, you should learn the concept of vector calculus, where we study the gradient, Jacobian, gradient descent, all those techniques come under this vector calculus. Next, again, that's what we have studied. Machine learning models are represented as mathematical functions. So we need to maximize or minimize the functions. That's why we talk about optimizations. So this is just an overview. Statistics. Where do we use statistics in machine learning? Statistics generally provides a lot of tools and techniques to extract meaningful insight from the data. Okay, to be very honestly speaking, in today's machine learning or in today's AI, statistics was earlier used. We just derive some of the concept, but it is very, very less used in machine learning today. So this gives an overview now. So I have been talking about some mathematical foundations here. Why now we got an idea why we have to study vector calculus, why we have to study linear algebra. This tells us, right? When you have machine learning data, we form it as a matrix. To play with matrix, we have to study linear algebra. So it's not that you have not studied it. Everything you have studied. You know about linear algebra. You have known about matrices. You have studied about matrix decomposition, matrix rank, determinant, trace, inverse. All those are covered here. Where do we use it? We'll see slowly. I'll give an mind map relation, how directly this linear regression is used in ML algorithms. We'll see that. You have studied about probability. We have studied about vector calculus, derivatives, partial derivatives, higher order derivatives, Jacobian, gradient, all we have studied. But how is it used? Let us explore that now. I hope you got an idea what all mathematics is required to understand machine learning. Tomorrow, maybe in tomorrow's session, you will study about supervised learning, one kind of machine learning. We will discuss it today. So when you go for that, you will have to, there the first thing is regression. That regression is not new, it's all available many years back in mathematics, regression analysis. Okay, so let's see how and where these concepts are used in. Just skip this and come back again. Yeah, see, I'm talking about linear algebra. So you know about the concept of vector, you know the matrix, you know vector space, matrix inverse, Gaussian elimination method. I'm not stressing on teaching all these things. These are all basic mathematics which is available in your academics. You might have studied system of linear equations, linear independence, basis. So these concepts, how are they linked? Let's see this. See, we have a vector. Vector generally represents linear independence. When we have vectors v1, v2, v3, v4, we verify whether they are linearly independent or dependent. Meaning, if using these two vectors, if I can find out other two vectors also, if there is a relation between v1, v2 for v3 and v4, then they are linearly dependent or otherwise independent. So that concept of linear dependence independence is used in basis, and basis is used in dimensionality reduction. Now, what is this dimensionality reduction? It's one important technique in machine learning. I will explain those things in simple terms. Right? This just to show you how and where this linear algebra is used in machine learning. Again, vector, set of vectors form matrix. Matrix represent linear mapping, which is used in classification of the data. Okay, so this here specifically we are talking about two important techniques. So linear algebra is directly used in classification and dimensionality reduction. What is dimensionality reduction? We'll see with an example. When you have a higher dimension data with you, when the matrix contains more number of rows and columns, right? What you try to do, each column here is a vector. Each column here is a vector. So v1, v2, v3, v4, v5. There are 5 columns. Maybe it is a 5 by 5 matrix. Then that becomes a 5. It has 5 vectors and 5 rows. So each vector, among these 5, I want to reduce the dimension. I don't want to have 5 vectors. I want to use only 3, or I want to use only 2. How to identify only those 2? Using the concept of linear independence. If these vectors, what is the relation between these 5 vectors? Can I write v2 equal to v1 plus 3 v3? If I can express this v2 equal to v1 plus 3 v3, v2 is not required. Only with v1 and v3 we can manage it. If I can find v5 equal to v1 minus 2 v3, v5 is also not required because I'm able to express, I'm able to find that with the help of v1 and v3. There is some relation between the vectors, right? So we are trying to avoid some vectors and we are reducing the dimensionality of the data set. So that is how this concept of vector, this concept of linear independence, and the concept of basis is used in dimensional reduction as well as classification. Let's see how analytical geometry is used in machine learning. So we talked about dot product, inner product, norm, length of a vector, distance of a vector between two vectors. We have studied about angle between two vectors in our academics. In your UG, PG, you might have studied mathematical courses where you might have studied all these concepts in mathematics. Dot product, cross product, inner product. Norm means the length. Norm means the length of the vector. Okay, so length of a vector, orthogonal projection, rotations, rotating a vector by 80 degree, 90 degree, 180 degree, all those we have seen. So these blue concepts we are already studied in mathematics. Where and how it is used, if you see, inner product, norm, the length, using norm we calculate the length, and this length is used in matrix decomposition. How? Let's see. I told you, when the data set is very large, very large, we cannot apply our mathematical concepts. I cannot find out rank, I cannot find out inverse of a matrix. It is challenging for us to do. So one alternate solution was to decompose the matrix, to break the matrix into small parts, not losing its original property. So for that, you need to know the length. You also should know the angle. These are used. Again, this norm, everything is used in regression analysis, and we use in same in dimensionality reduction as well. Even in classification, we use this inner product. Okay, so when you study this concept dimensionality reduction in the next coming days, when you study this, you will see the instructor or the speaker talking about the orthogonal projection, talking about the rotations of matrices, rotation of the vectors, angle between two vectors, how and where they are used. This clearly tells us. Next, matrix decomposition in machine learning, very important, very widely used. Matrix decomposition. Why? I told you, no, to break the large matrix into small. Matrix means to break the large data set into small data sets. To derive insights from the data set, I have to do matrix decomposition. So we know how to find out determinant of a matrix. We know how to find out eigenvalue, eigenvector, right? Diagonalization of a matrix, orthogonal matrix. We know all these things. So these concepts are used in, this is again, SVD is a singular value decomposition, one technique in matrix decompositions. It is used in dimensionality reduction. There is something called Cholesky decomposition. It is used in probability. Right? So these concepts of eigenvalue, eigenvector is not new for you. You might have heard since many years, and still maybe we are teaching and learning those things in our regular academics. Right? So these things are used in dimensionality reduction as well. I will give one proof in this session. I'll show you one proof of linear algebra, how it is used. We'll see that also. Okay. So vector calculus, again, partial derivative, Jacobian, Taylor series, difference coefficient. Again, this is normal differentiation. F dash of x, what we saw say here. This is dou f by dou x, partial derivative, right? So all these are used in optimization, widely used in optimization. Why? You have to find out the partial derivatives. You have to find out the first order derivative, then you have to find out the second order derivative, and you will check whether it is less than 0, greater than 0, right? Based on this, you will comment whether it's a maximum or minimum function. So this vector calculus is widely used in optimization, also in dimensionality reduction, regression. Mainly, this is used in regression as well as the optimization. Probability, one of the very important concepts what we read for in machine learning. So lot of things are there here: random variable, sum rule, product rule, Bayes theorem. You know very clearly Bayes theorem. We have something called naive-Bayes classifier. In machine learning, we have something called naive-Bayes classifier. So this is based on the Bayes theorem, what we have studied long back in probability. Okay, so this is how we can see that how probability is used in machine learning. Now let's see an example of linear algebra for machine learning. Before we move forward, I'll just give an idea about how and where. I just want to know if you have any doubts till now in this session, any queries till now, because we have seen an overview of what all is required, what all mathematics is required for machine learning by seeing basics of that. Right? I'll just now take you through the linear algebra alone, how this is used in machine learning. Yes, you can see, you are, if you feel you're not good at mathematics, it's maybe you're just making yourself low. You have studied mathematics so many times in different courses in your graduation. Nothing is new in this. I'll just show you. If you see the linear algebra concept, I'll just please listen to this one small module, that is linear algebra for machine learning. You will understand that whatever you have studied before is being used here. Nothing is new in this. ML is also not new. Once you see the ML algorithm regression, it's same as the regression analysis or the line equation what we have there in mathematics. Okay, so let's explore how linear algebra is used in machine learning directly. I'll take a small case study and example, and I will explain you. See here, there is one problem. So the input of my problem is wind speed of a turbine, and I have to identify how much power it is generating. A simple problem here. Wind speed. I think you might know about this such kind of turbines. Based on the wind speed, the power is generated. So my problem here, I want to identify how much power will be generated given the wind speed. Okay, so for this in machine learning, what we need some historical data. Maybe last 1 month or last 6 months data I need. When the wind speed was some x, what was the power generated? X1, what is the power generated? When the wind speed was x2, maybe when the wind speed is 10, the power is 5. When it is 15, that is some 6. When it is 25, it is somewhere 7. Like this, I need some data, historical data. Okay, so the problem, relation between wind speed and power output. Okay, see, so what we generally do, this is what the data I have with me. Okay, so if you see this graph here, so wind speed, when the wind speed is increasing, the power generation is also increasing. You can see these dark spots. This is some historical data what I have with me. So this is a simple line equation, right? This is drawing a line equation. So that is m into wind speed plus b equal to, that's what, mx plus c equal to y. A linear equation, line equation we already know. So m into wind speed, some quantity into wind speed plus a constant equal to the power generated. This is the line equation. Here, what is my input? My input is only wind speed. So nicely I'm able to identify it. Now, once I have this line equation, with me, if somebody asks me, when the wind speed is some 13.5, can you tell me what is the how much amount of power will be generated? You will just substitute that here. You already have an equation. The power generated y equal to some 3 into wind speed plus a constant 7. This could be simple, just an example. This is the power output equal to 3 into wind speed plus 7. How I got this equation? I got this equation. There are many techniques. You know how to write a line equation. Slope m y equal to mx plus c, x2 minus x1 by y2 minus y1. You can find out the slope. Using this, you can find out the slope and the constant. So again, we'll not see on that how to do that. ML model training, you will learn it in coming sessions. But in mathematical, if you see, this is a simple line equation. Y equal to, or the power output is equal to 3 into wind speed plus 7. So when I have this equation, anyone tells me, if someone asks me, or I want to make a prediction, given the wind speed, tell me what is the power generated output. I can easily tell that. Okay, this is fine here. Now, what if I say that the output, the power generation is not depending only on the wind speed? There is some other factor called temperature which plays a role. So now there are two inputs. One is the wind speed, second is the temperature. Because if it is raining, the wind speed might be low, or it is very cool, some fog is there, then the wind speed could be low, then the power output might fluctuate. Okay, so previously when it was only one parameter, my equation is very simple, y equal to mx plus c. Now the problem here is, it is depending on another factor also, that is temperature. How the line equation changed? My line equation changed to y equal to w1 x1 plus w2 x2 plus b, where x1 is the wind speed, x2 is the temperature. So I have to just find out w1, w2 and b using the historical data. Last 6 months or 1 week or 1 month data, whatever I have, using that I can build a model. I can build a line equation. I'm talking about line equation here, which we call as machine learning model also. So this is one ML model. Okay, right? So by this way, I got this. Next, if I go here, instead of 2, I have 4 features now. Wind speed, temperature, pressure, humidity. Power generation is depending on these 4 features. Then I'm getting the output. In that case, what will be my line equation? What will be my ML model look like? It is something like this. See, W1 into feature 1, that is wind speed, W2 into temperature, plus a constant W3 into humidity, plus a constant W4 into pressure. then I'm getting the output. So my line equation changed like this. Okay, so this is for one instance. One instance means today morning, this is just for today morning 10 a.m. data. 10 a.m. I have this data with me, right? But I want the historical data. I want to have a lot of data. So the equation becomes like this: W1x1, W2x2, so on, plus B equal to Y1. What is this data now? If you see, this is nothing but, again, at 10 a.m. This is at 11 a.m., 12 p.m., so on, 5 p.m. This data is recorded. Morning 10 a.m., the wind speed, what was the wind speed, what was the humidity, what is the temperature, what is the pressure. Based on that, what was the power generated. Again at 11 a.m., what was the wind speed, all those factors, what is the power generated, so on. So one full day data I have with me, that I am representing as line of equations like this. My goal here is to only find out the values of W1, W2, so on, and B. We have to find out the values of W and B. If we can find out this, we get one simple line equation. We get one standard line equation using which you can make predictions. So linear algebra is used for making prediction. So machine learning is used for prediction task. For predicting, we use the concept of linear algebra. Now, if you see this data, how am I writing it? See, wind speed, W1x1, W1x1, so on, W2, W2, so on. These are all how I am representing, and this is my target variable. Now, I can represent this data as form of a matrix. See, vector W1 into matrix which contains the actual data points plus B equal to the output what I know. So for ML model, what is the input given? You are given the matrix, you are given this vector, you have to find out this W and B. If you can find out this both, you get a line equation. That line equation is called as a machine learning model, which can help you in doing predictions. Right? So here we are talking about vector, matrix, matrix rank, matrix transformation, matrix decomposition, all we talk about here in linear algebra. So if you see the problem again from the whole, the problem was to given certain inputs, given certain parameters, you have to do a prediction what will be the power generated based on the temperature, humidity, pressure, and wind speed. That is the problem. So we are using machine learning for predictions. Right? So this is how the data set what we had, we have slowly converted that into a matrix or into a linear algebra concept. Now this, if I can solve it, this if I can solve this, I can if I can find out W and B, I get a model, I get an equation. That equation is called as a machine learning model or a regression model. We use it for prediction. So this way the linear algebra is used in machine learning. Likewise, all the concepts of mathematics are used in machine learning, what we have studied earlier. So again, a lot of things, again, I'll just skip this and move forward. We have seen a lot of, I'll just show you one example, how and where we use this. See, we study about rank of a matrix. This is a very popular known concept in or linear algebra. Rank, finding out rank of a matrix. This is used in image processing. When you are compressing the images, see, the original rank is 200. When you make the rank 1, the data is lost here. Why? What is rank of a matrix? If you ask me, number of non-zero rows, right? So again, in this is small 3 by 3 matrix. Okay, so rank of this matrix is 3 because the number of non-zero rows. If this is 0, still it is 3. If this becomes 0, the rank is 2. The data is lost. Like this, if I have this, still the rank is 2, the data is lost. So when the rank is less, you see, you cannot see that picture. When the rank is high, you are seeing the actual. So what is this matrix? Actually, it is the machine learning data. That ML data is representing this image. Again, I'm not going to computer vision, but actually each image contains a lot of pixels. Each pixel is again a 3 by 3 matrix. Each pixel, each dot here is a 3 by 3 matrix. So it's a combination of lot of small matrices. Again, this matrix concept is used in image processing as well. We talk about that there. We do dot product. We do a lot of operations in image processing. So when somebody is instructing you, or when you are learning about image processing, you or applications of ML into computer vision, you will talk about this matrix part there as well. Okay, so this is how linear algebra. I just want to show you how and where we use that into machine learning. So which concept should I know? Should I learn to learn linear algebra for machine learning easily? You have to talk about types of solution, Gaussian elimination method, row echelon form, reduced row echelon form, particular general solution. All these concepts are used. If you go for matrix decomposition, you should know about eigenvalue, eigen decomposition. You have studied it before. Matrix decomposition, Cholesky decomposition, eigenvalue, singular value decomposition. These are different techniques of matrix decompositions which are widely used in machine learning. Next, in vector calculus, you should talk about univariate functions, partial differentiations, gradients, Jacobian. You have studied this. You have studied about partial differentiation. You have studied about Jacobian, right? So maybe one or two are new in machine learning perspective, but they're all existing in long back in machine.
Sir, you are not audible, sir.
Sir, you are not audible.
Now am I audible?
Yes, sir. Yes, sir.
Yes, sir. Go ahead, please.
Sorry. So all these concepts of statistics are also used in machine. Just to show you how and where this mathematics is used in machine learning. Okay, so now let's go back and see the important ML algorithms. Just introducing them. You are going to study them in detail. So ML algorithms. We have till now we have seen what is machine learning, what mathematical foundations are required to understand machine learning algorithms, right? Now, in general, there are three types of machine learning algorithm. I'll focus very less on this because tomorrow's all discussion, the whole next week, you're going to study in detail about all these techniques. Okay, so I'll quickly show you about the different algorithms. We have supervised, unsupervised, and reinforcement learning. So we use this. What are these algorithms? To understand this, I'll just show you one simple terms. Okay, and we will discuss some ML algorithms in simple terms. Please understand this so that you know the difference between different algorithms and you understand them better in the coming sessions. The first one, linear regression. Okay, this is one ML algorithm. What is this linear regression? See an example. Imagine you are saving money every month to buy a bike. You want to purchase something, you are saving money every month. Okay, so linear regression helps you in guessing how many months of saving you need to, how many months you need to save the money so that you can purchase a bike. So for prediction, for guessing, for estimation, we use linear regression. This part is just to explain you what is the purpose of each algorithm. Okay, next, logistic regression. Okay, so here imagine you are deciding if it will rain or not based on the clouds. So you are seeing clouds on the sky and you want to decide whether it will rain or not. So logistic regression helps in predicting yes or no outcomes. Here if you see, I want to find out number of months I need to save the money. So it is some quantifiable value, maybe 10 months or 15 months or 2 years, something like that. So for prediction, for estimating a number, you go for linear regression. If you want to just estimate or guess yes or no kind of output, you go for logistic regression. Next, decision trees. So think of making a decision like choosing what to wear based on the weather. So if the weather outside, what is the weather condition? Based on that, you want to decide what to wear. For that, you can use a decision tree concept, where it will ask you a lot of questions. It will ask you a lot of yes or no questions and help you decide what to wear based on the weather. For such problems, we use decision tree concept. Support vector machine, right? What is this? Again, in simple terms, think of separating apples and oranges in a basket by drawing a straightest line possible. So there is a basket, it contains a lot of different oranges and apples, some fruits are there, you have to separate them, draw a straightest possible line to separate the apples and the oranges, right? So for that we use support vector machine. So SVM helps find the perfect line to tell them they are separate. Next, random forest. Okay, now this is very clever thing which we all have to follow in our day-to-day life also. So think of asking advice from many friends and combining their answers. Suppose you're unable to make a decision, what generally we do? We ask the same thing to many friends, and based on their answers, we decide, or we try to combine their answers and get the choose the most popular answer and take the decision, right? So random forest ask multiple decision trees and use the most popular answer. So very useful for our day-to-day life as well. Naive Bayes. So what is this? See, if you guess the flavor of the candy by its color, you are making prediction based on what you know. If I show you something in yellow color, you will say this is a mango chocolate. If I show something in the pink, you will say this is a strawberry chocolate. How you're telling it? You're telling it based on what you already know. So based on the past information. So whenever you're dealing with some problems where you know the past information, this could help you better, right? So Naive Bayes does this with math, predicting outcomes based on the past information. K-means clustering. What is this K-means clustering? So see a simple example. It's like sorting your toys into groups without being told the categories. You have to sort, given a basket full of toys, you have to separate them, you have to group them based on the categories. But what category is not told to you, you have to decide it and separate those data points or the toys in the basket. So for that, we use K-means algorithm. KNN, K nearest neighbors, right? So it is somewhat very similar to K-means clustering. Here also K nearest neighbor. See, it's like finding your favorite book by asking friends for recommendations. So instead of using, you are asking your friend what is their favorite book. So based on that, you are making a call whoever is the closest neighbor to you to make the prediction. PCA, principal component analysis, very important and very lot of ML algorithms or deep learning uses this concept, principal component analysis. See, it's very simple. You have a small piece of, you want to pack some clothes in this suitcase, right? So think of PCA as packing a suitcase. You have a lot of clothes, and PCA helps you fit the most important pieces into small space. So how you try to fit that clothes into the small place? How do you fit them exactly? Sometimes we don't arrange properly. No, you see in YouTube a lot of people showing how to arrange clothes in the bag or in suitcases very efficiently. So PCA does that actually. PCA helps us in identifying how to effectively store that data into that box in whatever available space we have. Gradient boosting. So it is like you are playing a game for the first time. When you play the game, you make mistakes there. Then what you try to do, you will try to rectify that mistake in the second attempt. Any games, like our children play lot of games, so he'll be learning from the mistakes. First time he will play, he will not understand the rule. Second time again he will improve. Third time, fourth time, fifth time, they keep improving, and after playing it 100, 500 times, they become master in that. So gradient boosting is also same. It is like improves predictions by learning from the past errors in small steps. Okay, when you're like how you correct yourself, in the same way you are trying to improve the predictions. If you have built an ML model, you want to improve its prediction capability, you have to use gradient boosting. Neural networks, right? It is same. We have already seen about neural networks. It mimics human brains. Like we learn concepts, computer will learn using help of neural networks, right? So neural networks are computer versions helping machines learn from examples. CNN and RNN. So CNN, your brain recognizes faces in photos. See, when you see somebody's photo, you will remember it for longer time. Why? That photo, that image is stored in your brain. You're able to understand that. You're able to store that information. So you may not know the name, but you will feel this fellow I have seen somewhere, right? So same is your CNN. What it does are specialized neural networks that help computer see and understand images. Okay, so you'll remember that. That's about CNN. RNN, see, when I am talking about a story of a movie which you already watched, you will immediately relate it to that story, right? So think of remembering a story by recalling previous sentences. I am starting one story. I'm telling introduction scene is like this, then so on. It goes, then this happens. Immediately you can relate. After 3-4 sentences I tell you, your mind is guessing what is that movie all about because you already watched it. So RNN is such kind of a thing. What we do here, RNNs help computer to see, understand sequences like text or time series data. So we play with those things. Autoencoders, very perfect. See, you have one page with you. This is widely used, in deep learning we use autoencoders. You have one page with you. You have taken printout of this. Okay, now you want to carry this paper with you, but you do not. It is raining. When it is raining, there is something written on this page. Okay, there is something written on this page. It is raining outside and you want to carry this paper with you. So what you generally do, you will try to fold this paper, you will make a small piece like this and you will put it somewhere inside the pocket. Okay, but after going back home, once you open this, is the information lost? Is the content written on that lost? No, it is as it is there, like that. Maybe the paper quality has reduced a little, but the content has not gone. It is same. Whatever matter, whatever message was there here, the same exists once you open the small packet. So autoencoders, actually what they do, you compress the big image, you compress a big image into a small tiny image. Then you play with that small tiny image. You do you apply all your techniques on that. Whatever you want to do, you'll do it the small tiny image. After that, you will again open it back. Right? For that, we use autoencoder. So autoencoders reduce data size and then reconstruct it. Bayesian networks, again, it uses probability to make predictions based on various factors, right? Like predicting weather by considering temperature and humidity. Same way, Bayesian networks will use probability to make predictions. Genetic algorithms. So this is like combining multiple brains. Think of creating a super pet by mixing traits of many different pets. So there is a breed, one kind of a dog, there is another breed B2, there is another breed B3. So what you can do, you can combine their best qualities of B1, best quality of B3, and you can form a new breed B4, right? So genetic algorithms evolve solutions by combining the best options over time. They keep evolving and find the better solutions. Reinforcement learning. So you might have watched a lot of funny memes about this reinforcement learning. So here what we do, we give training, we feed them, we reward them. Whenever they do good thing, we reward them. Whenever again they do good thing, keep rewarding them. If they are making mistakes, we have to correct it, right? So reinforcement learning helps computer learn by rewarding them for good actions and correcting their mistakes. Okay, so these are just different kinds of ML terminology what we have been what you will be learning in coming days. So this just to explain you what is each of this algorithm. Linear regression means you have to think about this example always. You have to save money. How many months I have to save? That will be that you will find out using linear regression. Whether it will rain or not, decision making kind of things. Whether you want to decide yes or no kind of questions, you have to go for logistic regression, right? If you want to separate the elements in a basket, you have to go for support vector machine. Like this, we have lot of these algorithms. I think you got a little idea about this, how and where we are going to use this. This gives an idea how to do that, right? So random forest, again in this, I'm just quickly recalling it again. Random forest, taking advice from many friends, meaning you're using multiple decision trees. This one tree, decision tree is one, multiple trees are there, it becomes forest. So what is decision tree again here? If you see, we are using by asking a lot of questions, yes or no questions, we are making a decision. We are making a choice by asking yes or no questions. So that combination we do in random forest. So all these are different techniques. I hope you got little idea about what is the purpose of each of these things with some simple terms, right? With some simple, silly examples to understand these terms. Okay, we have seen this. Let me move to the next concept. Any doubts in this ML algorithms in simple terms? Any queries here? Okay.
So, good evening, sir. It's a very
Yes.
nice session with a very insightful demonstration. And at that time, from the starting, actually, just we started to watch these sessions. Everything seems to be easily catchable, but after sometimes it seems to be get lost out of mind. So is it possible to share your PPT slides and video recordings also? Especially, sir, I request through
Yes,
this
will
platform.
be shared. Will be shared. After the session, it will be shared.
So I had some device glitch actually, so that is the reason I had some break also.
No problem.
Yes, sir. Thank you, sir. Thank you so much. Sir.
Okay. Okay. Right. So maybe next 5-10 minutes, we'll see how probability and distributions or statistics are used in machine learning. We have seen how linear algebra is used, right? Linear algebra, we have taken a small problem of power generation that we are trying to convert slowly with multiple features. Then we are converting that to line equation. So many line equations make one matrix. There we apply linear algebra concept to find out the W and B values. So we are able to form a line equation that is helping us to build a model. So now we'll see how probability and distributions or probability and statistics in specific, why are they useful and how we can use them in machine learning, how and where they are used in machine learning. Let us try to explore that. So these are a few concepts, right? See, in terms of machine learning, I will speak, then we'll come back to the basic concepts of probability and statistics. We are talking about two things in machine learning. One is data, other is model, right? So we are talking about data. When you have good data with you, you can form a better model, right? So in probability, we are given a model and asked what kind of data we are likely to see. You are given the model as the input and you are asked what kind of data we are likely to see. Whereas in statistics, we are given the data and asked what kind of model is likely to have generated it. So let's say statistics first. You are having some data with you. I have the BTech final year students data with me of all the branches. I have that student data with me. Okay, right? Given this data, which model might have generated this data? To find out that, we go for statistics. Whereas in probability, given a model and ask what kind of data we are likely to see, what kind of data will this model likely to generate, that we see in probability. Okay, now to understand this, again I'll go back to basic concepts of probability, right? So probability deals with predicting the likelihood of future events. Okay, statistics involves the analysis of frequency of past events. See, this is about future, this is about past. So when you talk about the past events, no, we use statistics. When you talk about future events, we use probability. These two keywords maybe you can remember and understand that. Let's see an example here. I'm not teaching you what is probability, but just see an example here. So there is one example to understand the difference between probability and statistics. See, consider there is a drawer containing 100 socks, 30, 20, and 50 of different colors. You can use probability to answer questions about the selection of the random sample. See here. See question number 1. What is the probability that we draw two blue socks and 2 red socks from the drawer? These kind of questions, given the data set already, that there is a basket, it contains some different data is already given. What is everything is given. We are asking what is the probability to get this data. Now, same example with statistics, you see. Same thing, right? Question 1, you see. A random sample of 10 socks from the drawer produced 1 blue, 4 red, 5 black. Then in reverse, I'm asking, what is the total count? Here, I'm giving the total count. I'm asking, what is the probability to get 2 blue, 2 red? Here I'm telling, I have drawn randomly, I have picked up some 10 socks from that. I got 1 blue, 4 red, and 5 black. Then, using this data, tell me total how many are there in that basket. Reverse of that. Okay, so these kind of questions are used in statistics. So I hope you got it now. But in terms of machine learning, I'll show you how and where it is used. But just to differentiate between probability and statistics application in machine learning. That's why I said no. This is widely used, but this is very less applicable in today's ML models what we have, because lot of advanced techniques have come instead of doing the traditional way of analyzing or deriving the insight from the statistical data. So in probability, we are given a model is already given. We are asking what kind of data we are likely to see. Whereas here, given the data, what kind of model we are likely to generate. Okay, so again, all these basic concepts of random variable, I just go to an example. I think this is all basics of probability: marginal, joint probability, conditional probability, right? Discrete and random independent. I'll just quickly go through an example. Yeah, see this. How this probability is used, let us see. So again, I have one data set with me. I have some data set of some different kinds of insects. Katydids and grasshoppers are 2 different kinds of insects. Okay, so this is the existing data. Already I have this data with me, which are labeled. It means these are katydids. These kind of insects are grasshoppers. Now I give a new insect like this, and I'm asking you whether this is of type 1 or type 2. Whether this is type 1 or type, means predicting, guessing, making a guess whether this is type 1 or type 2. So I cannot exactly say, but normally as human beings, if you see, this insect looks same like this because its leg is here, its leg is like this, or it is like this, I can say it is katydid. Also, I could see this antenna here, this tower. If you see here, there is one big antenna here. Here also we have antennas, but this insect does not have antennas. But here they have antennas. You see, every insect has antennas. So I am unable to guess whether it is of type 1 or type 2. Maybe more chances it is type 1, less chances it is type 2, something like that. Maybe I can say it is 70% type 1 and 30% type 2. Since it is not clear, since it is uncertainty is there, we are not sure about this, we talk about probability. So this is one classification problem. Okay, identifying the given insect, whether it is of type 1 or type 2. How we use probability here, let us see. So for that, we have to understand the features of that insect. Okay, so there is something called antenna length, there is something called abdomen length, the stomach length, there is something called the leg length. Like this, we have so many options. Let's take only few of them, right? So I'm talking only about the abdomen length and the antenna length, these 2 parameters. So I found of the 10 insects, no, we have 10 insects here, right? This 5 and this 5. So this 5 data I have with me like this. So first insect, abdomen length is 2.7, antenna length is this, it is grasshopper. I know that already. By seeing this, if you observe, there is some pattern here. Now, this is the existing data, what I have. The 11th one, what I'm giving here is, given abdomen length as 5.1 and antenna length as 7, tell me what it is. I want to make a prediction. I want to make a classification. I want to classify and tell whether it belongs to type 1 and type 2. If you make an observation here, you see antenna length, abdomen length for all grasshoppers is less than 5. See 2.1, 0.5. It is less than 3. For all grasshoppers, abdomen length is less than 3. And antenna length also, if you see 5.5, 4.7, 3.1, 1.9. So it's all less than 5.5 antenna length. Okay, this is for grasshopper. And if you see for katydid, abdomen length 8, 5.4, 6.1, 8.3, 8.1, means abdomen length is greater than 5 for the cathetid. Now, when abdomen length is 5.1, I can quickly say it is cathetid, but no. But here this is 7, right? So it is different. So I'm unable to make a guess whether it is a grasshopper or cathetid. So what we quickly do, we'll plot the data, we'll again summarize that, and we'll plot this distribution of the data. We'll see how the data is distributed. See, I'll just quickly, I did the plotting of the data. With a lot of data, we can build histogram. Let us use antenna length only. Now I have used antenna length only to plot that. So this is antenna length of the type 1. These are the antenna lengths of type 2 insects. If I plot them, it looks something like this, right? Two normal distributions for visualization. Now, from this visualization, now what is the question given to us? What is the question given to us, right? If somebody asks us, if the antenna length is 3, which insect is that? So this is the data point, which antenna length 3. So it is covering, it is where it is there, in which region is it covering more? That we have to use it. See, so for that, if you see the data point 3, this is 2, this is 10. With that, I came to know that more probability of being a grasshopper is 0.833, being a cathetid is just 0.16. You can easily identify that here. See, this point here, this is the curve. So this point is somewhere in the middle. But for the red color one, if you see, it is at the very corner. So high chances it is grasshopper only, not the cathetid. But if I give the length as 7, the point is somewhere here. So it is very less in the blue curve and very more in the red curve. That's why 750, the probability. So 0.75 probability that it is cathetid, or 75% probability that it is cathetid. So that we are able to do it, right? So using these concepts of probability, we are trying to apply this is what we use in classification problem. This is one classification problem. Classify this insect as cathetid or grasshopper. We use probability methods here to do the classification. Classification, again, very important concept in machine learning, right? So it goes on. There are a lot of things to learn in probability and statistics. No, random variable variance, covariance, and correlation, lot of things, and these distributions, what we have seen in our mathematics. These are all not new. We have studied them. Only thing, how and where they are used. If you are reading some research papers, you will come to know all these terms are being quoted in those papers. So if you are strong at mathematics, only then you can understand and do well in machine learning algorithms. In next week's sessions, in tomorrow onwards, whatever session you have, everywhere you will see the speakers talking about mathematical stuff, because you know those concepts, you have studied these concepts, everything will be understood to you there. So I hope I just tried to cover you, create an awareness which all concepts of mathematics are used in machine learning through this session. So any queries, if you have, I'm ready to answer. We have just 2-3 minutes left for our session.
Yes, sir. Thank you, first of all, for a very interesting and insightful session. The explanations were really very nice. But my question is that, sir, I'm hearing a word like KNN, that is Kolmogorov-Arnold network. So if you can throw some light on that, what is Kolmogorov-Arnold network is there? Is it a part of neural network, or what it is? What is KAN? KAN.
This I also didn't heard. I'm sorry for this.
Okay, sir. And sir, another question is that when you have a larger CSV file with a lot of rows and columns, so which of the machine learning, like whatever you have told, like linear regression, logistic, decision tree, so which will be a better method out of all that to get to a better prediction?
See, all these ML models, irrespective of the data size, whether it is big or small, we can go for machine learning. But if the data is complex, meaning it has lot of features,
yes,
and then we have to go switch for deep learning.
Deep learning.
Deep learning. see, again, it's not exactly true, but it is believed and it is learned from experiences that the data size is small, you apply ML algorithms. If the data size is large, you can go for deep learning. Even whatever the regression does, a small simple regression concept does, same thing can be done by a deep learning model as well.
Sir, you also mentioned about matrix decomposition. So if you have a very large data set, like
Yes.
if you have like suppose 50 or 70 features in
Yes.
that, so
Yes.
how can that matrix decomposition means how that features will be divided into smaller matrices?
That's what-
Like on what?
this is one beautiful thing in mathematics or machine this linear algebra is matrix decomposition. There, you suppose you have a 10 by 10 matrix. You
Yes.
found out its eigenvalue, eigenvector. Maybe, for example, x, y, z are the eigenvalues for that big matrix. Okay. So when you decompose it, you get three other matrices. Maybe you can break that into three separate matrices or break that into two separate matrices. After breaking down into 2, 3, or 4 small matrices, you will still get the same XYZ values for those matrices. So these techniques are very intelligent that you break down them into small pieces such that their original property is not lost. That's why we use these decompositions in computer vision and image processing. When you have a large image with you or large data with you, you try to break down into small things. You play with that. Again, nothing is lost. It is same, the original thing, what you are playing with it.
Means you recombine the same thing at the end.
Only thing I cannot apply my operations on large thing. I am
Yes.
breaking down into small, and I'm applying and getting the answer. If you can again combine them, you get the same answer as the large one.
But sir, if something is like that, suppose I'm not sure if that's the correct question, but if suppose there are 50 features and if we divided our matrices and suppose there is an attack detection which is based on some important features and all those features are coming in one matrices only, then how this other three matrices or any
Yes.
other, how the recombination will affect like
Right,
the
right.
prediction?
That's what I understand. So that's what, no, when the data set is only numerical data, only then we can apply. First thing is that if the data set is purely numerical, I can convert that into a matrix and play with it. That is one. Second one, decomposition, where you have to do. Is it, we are not losing the feature. I'm not worried about the feature. I just want to find out the average of that matrix, or I want to find out the product of that matrix. Then only I go for those things. See, we exactly don't, like you said, practically, we don't
Yes.
actually break down and do it. Maybe in a large ML algorithm, this step is used in between to break down, again combine it back.
Because I have read many research papers. See, I'm also doing my research in IoT network. So a lot of we have a very large data set, but this matrix decomposition kind of a thing I have not heard in any research paper as such now. So I was thinking if that can be used or not, because if the features get selected in just one matrices, then how that correlation between the other matrices will affect the prediction.
If you read some image processing paper,
Image processing must be different. I am working on a CSV data set.
Yes.
So
Image processing, if you see, we talk more about singular value. SVD is widely used. I read some papers on those things where SVD is used there. Maybe for your data, you can apply it. Only thing you should know how is this syncing with.
Okay, thank you so much, sir. Very nice session, sir. Thank you so much.
Yes.
Sir,
Yes, please.
sir, this is Anupama. I had a doubt, sir, not exactly matching to the content of the presentation. I
Okay.
had a doubt, like, say, for example, if I am training the machine. So now when I'm using a machine and say I'm sitting in front, a person is sitting in front of a machine, and say you try to detect that the person who is using that machine is a human. Like, say, for example, you're giving a captcha or you're giving some kind of a, say, whenever you try to access the Google contents, it'll ask for you to tick the contents, particular contents, like tick the parts of the square
Yes.
where it is a motorcycle. That belongs to deep learning, or it is neural network, or what kind of this one? It does any of these link to that?
Thing is that actually it just want to verify. See, our human brain, we know we will actually, that can be replaced with a good question. Even see that particular system is asking you to select those particular parts to validate that you are a human being, not a machine, because it is posing some set of questions it is showing you some pictures and you only can easily identify it. But even today's AI models have been built which can detect it. So it is linked to the deep learning or the generative AI models, which can detect those images and can, they can do it automatically. So it is going to come. That's why the people who are posing such kind of questions to us are being more careful now, so that even the machine cannot detect it.
That means a human who is training a machine, and then further a machine is testing whether a human is using the machine.
Correct. True.
Okay, sir. Okay. So they everywhere normally, and I thought might be it is linking to, like, because sometimes if a blind person is using a particular this one and logging in, there is again a voice message also in that.
Yes,
The
yes.
person can click the voice and also listen to it
True.
and try to log in, because there are many security issues coming on. So I thought whether it is belonging to deep learning linked to cyber security, or blockchain, or any of the advanced methods for securitizing data. So I had a doubt in that.
Okay.
Thank you, sir. Thank you.
Anandraj sir, Vinay sir.
Hello, sir.
Sir, I personally have a lot of confusion in identifying the importance of eigenvectors and eigenvalues in the context of the machine learning algorithms. We are very much aware of finding those eigenvalues and eigenvectors in the context of mathematical
Yes.
problems. During our BTech first year, second year days, or in our intermediate days, we used to find very fluently about the values of eigenvalues and eigenvectors given a matrix, 3x3 matrix or 4x4 matrix. But
Yes.
now in the context of the machine learning algorithm, the data size is very huge, n by n.
Yes.
Right? For example, the data set is very much large, right? So in that context,
Yes.
how do you, how does the concept of eigenvalue and eigenvector play a role? What is the importance of that, and how to find them? Can you please throw
Yes.
some light on that on a separate session, not now, or web
Yes.
talk?
Yes.
Right? People will feel confused with this. People often feel confused about the data and the eigenvalues and eigenvectors. Can you please correlate those two areas?
Yes,
Not
sir.
now,
Generally,
not now, sir.
yeah.
You
Yes.
please take
Yes.
some time,
Definitely.
and
I understand. I understand, sir.
I speak to the Sadanam sir, and that because I see a lot of, I observe a lot of enthusiasm from across the participants. Most of the participants are applauding your presentation. It's very good.
Thank
But
you, sir.
at the same time, you please do what I request for.
Definitely, sir.
Right. Thank you. Thank you, sir. Sayanam
Thank you.
sir.
Yes, good evening, sir.
Yes.
Chandu, is it Chandu?
Yes, sir. Yes, sir.
Yeah, Chandu, please go ahead. Go ahead with
Okay.
photo thanks.
Okay, sir. Okay, sir. Good evening, sir. Good evening, all. I would like to sincerely thank sir. I would like to sincerely thank sir for your wonderful session on fundamentals of machine learning. Your talk made it is clear and how important of mathematics is understanding and working with these models. And you also highlighted the difference between statistics and probability, which help us to see how these concepts play a key role in building machine learning models. And you explained how to collect the features from the real world problem that has given approaching how real world challenges is effectively collected. Thank you for sharing your knowledge and making this session so interesting and valuable for all us, sir. Once again, thank you, sir, for your time and effort.
Thank you so much. I would like to thank all the coordinators for this opportunity. Hope to meet you again sometime. Thank you all. Good night.
Thank you,
Good
Vinay
night.
sir.
Thank you, sir.
Yes, all the participants. Tomorrow the session will start exactly at 6 p.m. And all these FTP PPTs will share to you after completion of all the sessions. Thank you, guys.